In this video, we will take a look at Ablation-Cam. The inspiration for Ablation-Cam comes from GradCam, so be sure to check out the previous video to better understand Ablation-Cam. Just like GradCam, Ablation-Cam visual explanations can be generated for any layer L, but it is usually taken to be the last layer. We will pick up from the activation maps of layer L. The squares can be thought of as activation maps. A1, A2 and AK are the convolutional outputs after layer L. These activation maps are used to get the final output vector Y. The steps to get the output vector Y from the activation maps can be compressed into a composite function, say f. The visual explanations are generated for a particular class C. Or put another way, we are trying to answer what does the model look at when its output is, say, dog. Therefore, we only take the output pertaining to a particular class C, YC, which we call the class activation. If you are familiar with GradCam, you know that visual explanation is nothing but a weighted sum of activation maps. Therefore, the next natural step is to compute these activation map specific weights. In GradCam, this weight is the partial derivative of the class activation with respect to a spatial location ij. This is where the novelty of Ablation-Cam comes in. Here we set the activation of the spatial location ij for a activation map k to 0, or in other words, ablate it to get an approximate slope. If we consider this ablation on the scale of an activation map, the effect is very intuitive. The importance of an activation map is the change it creates upon its ablation. The function f is just a placeholder for class activation yc. Ablated class activation is denoted yck. Here, the norm term in the denominator tends to be very large compared to the numerator. Therefore, it is replaced by yc. The weight term can now be read as a fractional change in yc upon the ablation of activation map k. Putting everything in the final form, we get a familiar looking formulation as we saw in GradCam.